Okay, subtopic 3.7, electrical energy and power. So in this subtopic, we will discuss two linear outcomes, and the first one is use power. Use the equation of power, P equals to IV, right? And P equals to I square R, and the last one is P equals to V square over R. And second linear outcome is electrical energy, and the equation for this energy, work or W, or energy, equals to VIT. Look at to the explanation about your electrical energy. Right, as we know, electric energy or electrical energy is useful to us because it can transform into other forms of energy, because as we know, energy cannot be destroyed. So electric energy can be changed in other form of energy. It can be in thermal energy or light. Because at night usually we use the lamp and so on, so you have the light. Next, according to the conservation of energy, all the energy delivered to the charge carriers by the battery must be lost in the circuit, right? Because the main source comes from the battery. So once your electron, this charge carrier refer to your electrons flowing in our circuit. So once your electrons flows in the circuit, and energy will be lost in the circuit, which is usually related with the drop voltage. That is a charge carrier traversing in the circuit must lose all the electrical potential energy it gained from the battery when that carrier returns to the negative terminal of the battery. Like this. I will draw it for you. This is your battery and connected through two resistors right here. You have R1, you have R2, and this is your battery. I label with the EMF, right? And as we know, for the battery or any power supply, it has two terminals, terminal positive and negative, and of course your electron would be flow from negative terminal to the positive terminal, right? So your electron flows from the negatively terminal of the battery. It means your electron gain the energy from the battery. Look at to the second sentences. Energy delivered to the charge carriers, your electron, by the battery. So your electron gain energy from the battery, and then your electron will be flow across your resistor 2 and also resistor 1, and it will produce the drop voltage. So that's why your energy from the battery will be lost in the circuit, as mentioned in our third statement. Your charge carrier traversing the circuit must lose all the electrical potential energy that it gained from the battery when your electron return to the negative terminal. Okay? The electrical energy or electrical potential energy, which is work, or you can use the symbol of capital E, is the energy gained by the charge from a voltage source, which is battery, having a terminal voltage. Okay, because you can see it from the definition of electric potential from chapter 1 electrostatic. So electric potential is V equals to the work done to bring a charge from infinity to a point per unit. That's charge. So that's the definition of electric potential. So work is our electric potential energy. Okay, work is our electrical potential energy. So that's why work is energy gained by the charge from a voltage source, which is battery, can have the terminal voltage. Okay, from the definition itself. So then you just rearrange your equation, make it your work as the subject. So work equal to QV, Q times with the V. So this is our work done by the source on the charge. And refer to the definition of current. As we know, current is the rate of charge flow in the whole circuit. Okay, dq over dt, and you can simplify or rearrange your equation. Q equals to IT. Then we substitute your Q into the equation of work. Okay, so then once you substitute, you can have the equation of work equals to VIT. Okay, just substitute Q into W. Okay, like this lah. W equals to Q is IT. Okay, times with the V. So you can have VIT. And as we know, the unit for energy. Okay, so that's the basic unit. Work or energy must be in joule. Okay, should be in joule. So that's the unit of work. Okay. Rate of energy. Rate of energy delivered to the external circuit by the battery is called as electric power. Okay, because rate, okay, rate refer to time. Okay, refer to the time, over with time. So energy over with the time delivered to the external circuit we call as electric power, and represented with this equation. Okay, power equals to work over time from the from chapter 5 in semester 1. Okay, power is rate of work done, right? Okay, W over T, and we know that work equal to QV over with the T. Okay, work is QV over with the T, and Q equals to IT. Then we just substitute lah. Okay, just substitute. Power equals to, okay, I change Q as the IT. So this is IT, V over with the T, and you can cancel your time. Okay, end up you can have IV lah. Okay, so that's how we get the equation of P equals to IV. P equal to IV is our standard equation to find the power. Okay, but if you want to find the power in the battery, okay, power in the battery, this is for the battery. Okay, for the battery, we just change your V with EMF. Okay, if you want to find the power inside the battery, we just use P equal to IEMF. Okay, okay. This is the unit for the power is watt. Okay, the unit is watt. Okay, to determine the energy dissipated per second in an electric device, or rate of energy dissipated, okay, rate of energy dissipated is given as, okay, you can use the general equation, which is P equals to W over T, or you can use P equal to IV, depends on information. This is our general equation. Okay, take note. You can use P equal to IV to find the power from the battery, and also you can use P equal to IV to find energy dissipated per second. But you need to be careful about energy dissipated. Okay, why? Okay, like this. A passive resistor, okay, let's say we have a passive resistor, is a resistor which converts all the electrical energy into heat. So that's we call as a passive resistor. For example, a metal wire. Okay, your equation, it can be like this. We use your general equation, P equals to IV. We use P equal to IV. And we want to find the energy dissipated per second, right? Means power loss. Okay, power loss is just caused by resistor. Okay, power loss in circuit, it is caused by the resistor. So it can be by wire or anything which has the resistance lah. Okay, which has the resistance. Okay, so basically we know that V equal to IR. Okay, your V equal to IR, and then you can substitute V equal to IR into IV. Okay, like this. P equals to IV and V equal to IR, right? So IR. So then you can have our second equation, power equal to I square R. And the other one, okay, okay, I box the equations. Okay, our second equation is P equals to IV, and I change I, so I is equal to V over R. So V over R from the Ohm's law. Okay, from the Ohm's law, V. Okay, so V is square lah. So V square over R. Then you can have our third equation. Okay. So basically you have three different equations to find power. Power equal to IV. Okay, power equal to IV, this one. Power equal to I square R, and power equal to V square over R. But if, I repeat once again, if you want to find the power loss or power dissipated, means it is caused by the resistor. So it's better for us, we use I square R and also V square over R instead of IV. Okay, it's better. Okay, so that's why we mark here, this is only for the resistor. Okay, for the dissipation. Okay, to find dissipation power. Okay, that's it for electrical energy and power. Okay, this is the conclusion about the equation of power, because most of the students a bit confused how to use the equation of power. So I will try my best to explain about the equation of power. Okay, right now you have three different equations. Okay, you have three different equations. Equation number 1, P equal to IV. Equation number 2, P equals to I square R. Equation number 3, P equals to V square over R. Okay, if you want to find the power supply, okay, the power supply means from the battery. Okay, from the battery. Just use equation number 1. Okay, use equation number 1, IV, because you can change your equation. Okay, you can change your equation. Okay, P equals to I EMF, because from the battery. Okay, next, if you want to find the power dissipated, okay, the power dissipated or power loss. Okay, as I told you just now, it is caused by resistor, only resistor. Okay, because it is heating up. Okay, now look at the equation number 2 and number 3. Both equations have the R. Okay, we have R right here. That's why I advise you, if you want to find the power loss, just use I square R or V square over R. Okay, but if you want to use equation number 3, make sure that your V, okay, make sure that your V must be V across resistor, okay, not the battery. Okay, not the battery. Okay, remember that. Same goes equation number 1 actually. Okay, if you want to use P equal to IV to determine the power loss, okay, you have the V also right here. Make sure your V is the V across resistor. That's it. Just be careful with your potential, okay, with your electric potential V. Okay. Okay, next we go through for 3.8, subtopic 3.8, potential divider, and we have two linear outcomes right here. Okay, A, explain the principle of a potential divider, and second, use equation of potential divider given as V1 equals to bracket R1 over with R1 plus R2 times with the total voltage. Potential divider. What is the potential divider? Okay, potential divider is a fraction. Okay, is a fraction of voltage supplied by a source of EMF. In simple words, potential divider is a method. Okay, is a method to find V. Okay, to find potential, electric potential, without find the current. Okay, this is a method actually. That's why potential divider is a fraction. Okay, is a fraction. Fraction is bahagi, ratio. Okay. Okay, and we have the condition to use the potential divider. Okay, if you want to use the potential divider to find the V, make sure your resistors are connected in series. Okay, your resistor should be connected in series, cannot be in parallel, okay? Right? Why? Because, okay, because current flows in each resistor is same. Okay, as I told you, as I write right here, okay, as I wrote right here, you need to find the V, okay, find the V without find the current. So that's why your current should be have the same current, because it is the ratio and you can cancel out your current. Okay, we will discuss later. Okay, let's say this is your simple circuit, right? You have, okay, you have a battery connected through two resistors, R1 and also R2, and it is in series connection. Okay, in series connection, and of course you have the current flow. Okay, so this is your current flow, flows like this. Okay, circle in anti-clockwise. Okay, because arrangement of your battery. So this is your V1, V across resistor 1, and this is V2, V across resistor 2. Okay, and now we can see that your resistor are connected in series. Okay, in series. So you can use the potential divider. It is the shortcut. Okay, now to find the equivalent, okay, to find the equivalent resistance, because it is in series, so R1 plus with R2 lah. Okay, R1 plus with R2, and based on the Ohm's law, to find the current V equals to, sorry, I equals to V over R. Okay, by using the equation of Ohm's law, I equal to V over R. Okay, then just substitute your equivalent resistance, R1 plus with R2, inside the equation of Ohm's law. So you can have I equals to V over R1 plus with R2. Okay, and if you want to find the potential, okay, potential difference across R1, okay, we need to find the V across R1, this resistor, okay, resistor 1. So back to the basic, we also use the equation of Ohm's law. Okay, the equation of Ohm's law, V1 equal to IR1, and because of current is the same current, okay, it's the same current, so we just substitute this equation into this one lah. Okay, just substitute the equation of current into V1 equals to IR1. Okay, and now your equation become V1 equals to R1 over R1 plus with R2 times with the V. This V, guys, okay, this V is our total V. Okay, total V from the battery. Okay, from the battery. Or you can see it like this lah. Okay, I make it simple. Okay, right now I want to do the ratio between V1 and V total. Okay, V total. So based on the Ohm's law equation, V equal to IR, isn't it? So this is IR1 lah, IR1, and over with I, V total is R total lah. So R total is R1 plus with R2, and it is in series. Once again, I repeat, this is in series. Once your resistors are connected in series, you can cancel out your current. So you can have this type of equation. Okay? Clear. Okay, now if we change both resistors with a wire, okay, so resistance R1 and R2 right now are changed with a uniform homogeneous wire, because as we know, wire also got the resistance. Okay, right, so your circuit become like this. Okay, you have the battery and you have a wire AB. Okay, wire AB. AB is a same wire. Okay, AB is the same wire. Okay, the same wire. So you have the same. Therefore, the resistivity and your cross-sectional area are constant. Okay, are constant. It is the same because involve the same wire. Okay, and now we divide or split your wire into two parts. Okay, AC and also CB. So AC have its own length, which is L1. CB also has its own length, L2. And of course, our potential difference, potential difference differ for V1 and also V2. Alright. And since we change the component resistor with a wire, and you can determine the resistance of a wire, okay? You can find it because wire is unknown resistance. So you can find it using the resistivity and so on. So the resistance of a wire given by rho L over A. Okay, rho L over A. So rho is the resistivity of a wire, L is the length, and A is the cross-sectional area. Okay, and because you already divide into two parts, and we have R1 and also R2. Okay, then we substitute into our first equation that we had discussed just now. Okay, V1 equals to R1 over R1 plus with R2 times with the V total. So just substitute. Okay, just substitute this R into this one. Okay, so once you substitute to find the potential difference across your L1. Okay, similar with R1 lah. Okay, but we do not know the value of R1. That's why we change with L. Okay, why? Because it is a wire. Okay, because it is a wire. Allah. Okay, sorry, because this is wire. Okay, so now after you change your equation, okay, your first equation with your R, okay, rho L over A, end up you can have this type of equation. V1, V across L1 equals to bracket L1 over with L1 plus with L2 times with V total. Okay, to make it clear, okay, I will derive for you. So this is V1 equals to, okay, equals to your R1 is rho L1 over A, right? Over with R1 is rho L1 over A plus with rho L2 over A. Okay, times with your V total. So now, because I had mentioned this before, you have the same wire, resistivity and cross-sectional area are constant, so you can cancel out your rho and also your area. So end up finally, you can have this type of equation. Okay, simple. It is like, looks like similar to each other. Okay, just change your R become as L because it is directly proportional. Okay,